So let's start with the concept of what is a limit. Now, limit is a very important concept in maths because it helps us to understand a lot of things that are traditionally undefined. For example, let's try to build up on this concept step by step. So let's say we have an equation y is equals to 1 minus x squared divided by 1 minus x. Now you can simplify this equation into 1 plus x, 1 minus x, and divided by 1 minus x, right? And you might feel that should I cancel this out, and you would get 1 plus x. Now this sort of form 1 plus x is valid, but it is not valid for a certain x value. So this is basically an incomplete statement because this is not true for all values of x. For example, if I say that x is equals to 1, if I say that when x is equals to 1, then if what will be the y value? So if you plug x equals to 1 in the equation of y, you would get y is equals to 1 minus 1 squared divided by 1 minus 1, which is 0 divided by 0. And 0 divided by 0 is basically undefined. This is undefined, which means that no one knows this answer. Why is that? Because see, it's a very simple explanation. Because see, if we have 10 divided by 2, we write it as 5. And this 5 means that we are adding 2 to itself total 5 times. We are adding 2 to itself total 5 times so that we get 10. So similarly, if we write 0 divided by 0, it means that how many times should I add 0 to itself so that I get 0? Now the answer is quite weird, because you can add 0 to itself many times and you would end up getting a 0. For example, you would add 0 to itself once, so basically you're adding 0 twice and you're getting 0. Or you could add 0 to itself 4 times and you would again get 0. So there is no definite answer, because this is telling us that we can add 0 4 times. So it's telling us that 0 divided by 0 should be equals to 4, and this is telling us that 0 divided by 0 should be equals to 2. So there are basically infinite ways you can divide 0 with itself and you would get the same result. So we call this that this thing is undefined. Also, anything divided by 0 is undefined, because let's say I have 10 divided by 0. Now this 10 divided by 0 means how many times should I add 0 to itself so that I get 10 as the answer. And it's quite obvious that how many times, no matter how many times you add 0 to itself, you are never going to get 10. So no one knows what this value is, right? So we are calling this value undefined. And when we are facing this problem of getting undefined values, the power of limit comes in. So limit basically helps us to study the region where a function becomes undefined. So let's look at this equation y equals to 1 by x. Now, if x approaches towards 0, as you can see, the y value is basically skyrocketing towards infinity. So what we can say is that when x is approaching towards 0, then y is approaching towards infinity, right? So we can directly say that when x equals to 0, y equals to infinity. This statement is wrong because we don't know that what the exact value of y is when x is exactly equals to 0. What we can do is we can only see where it is trying to go. So that's basically what a limit says. You can also think of limits as magnifying glasses, which basically zooms at a particular point and tries to see what is happening there. So here I have an example that we have just previously seen, that is y equals to 1 minus x squared divided by 1 minus x. Now here is the graph of this equation, and if you look closely in the graph, you will realize that there's a small, I think the quality is not so good, so let me just sketch it again. So at this particular point, when x is equals to 1, you can see there is an open circle over here, which basically indicates that there is no exact value at this region. We don't know what this exact value is, right? Because when x is equals to 1, this function is undefined. But we can see that this value, this y value, is trying to go towards y is equals to 2. And if you plot some points for this equation, for example, when x is equals to 0, you're seeing that y is equals to 1. Similarly, when you're trying to go closer to x equals to 1, so remember our target is we are trying to approach when x is approaching to 1. All right, so from 0 we have moved to 0.5, and we can see that y have moved to 1.5. Similarly, when x has moved to 0.9, y has moved to 1.9. And when you are closing down more and more towards x equals to 1, you are closing down towards y is equals to 2. See, when x is equals to 0.999, y is equals to 1.999. But when x is exactly equals to 1, y is undefined. So we can see the tendency of the function, that is, it is trying to reach towards 2, but it can't reach exactly at 2. So what we say is, we say that limit as x is approaching towards 1, that equation we have just discussed, which is 1 minus x squared divided by 1 minus x, this whole expression is reaching towards 2. So remember, this doesn't mean that when x is equals to 1, y is equals to 2. It simply means that when x is trying to go towards 1, y value is trying to reach towards 2. So here's a detailed way of the notation that we're going to see. That is, when we have a function, let's say for example we have a function f of x, we will write the f of x in the middle, and on the left hand side of f of x we will write the limit notation. And limit notation is basically lim, which stands for limit. And under the limit notation we are going to write the x value that the function is trying to approach, right? That is basically the independent value, the value that we are trying to go towards, and the value which we are approaching at the end is on the right hand side of the equal sign, that is z. So z basically says the y value we are getting close to as x is getting close to n, right? So for the previous example, it was when x was trying to go towards 1, the y value, which is the expression over here, 1 minus x squared divided by 1 minus x, this whole expression is trying to go towards 2. Now limit is very important because we're just gonna we will be discussing soon what a derivative is, so you will need this concept of limits. Here we have a function f of x. I have just simply sketched a random curve. It doesn't imply any specific equation. So this is our x-axis and this is our y-axis. Now let's try to take a closer look at a specific point. Let's say we are trying to study this specific point over here. Let's call this point x, comma f of x. Now x implies this x value and f of x implies this y value, which is basically the height. This height is f of x, all right? And let's try to take another point on the same function, and basically what we are going to do is we are going to take another point that is some h distance from x. So if this is x and let's move to some h distance, let's say this distance over here is h, and then this x value would be x plus h, and this point on the curve would be here, which is x plus h, and the corresponding y value would be f of x plus h, because remember f of x plus h basically shows us the y value at this x value. So now the idea is something like this. We're going to connect these 2 points with a straight line. Now this line we have just sketched here is basically a normal straight line. So we can find the we can find the gradient of this straight line using the simple straight linear gradient formula. So the gradient's formula is y2 minus y1 divided by x2 minus x1. and here y2 is basically this thing, and y1 is basically this thing, f of x, all right? And this would be my x2 and this would be my x1. So for this pink line over here, I can say that the gradient of this pink line would be f of x plus h, which is y2, minus f of x, and divided by x plus h minus x. This is basically the x2 value and this is basically the x1 value, all right? So this whole expression over here would give us the gradient of this pink line. Now till now we haven't done anything new, but now what we are gonna do is we are gonna use the concept of limit we just explored some moments ago. Now what if we decrease the h distance? Instead of this whole h distance, what if we made this h distance only this much, just this much? So instead of this whole pink line, let me just erase it and sorry. So let's say that this h has become this new blue line. So instead of this whole big line, the new h would be this small distance, all right? So if that's the case, then the point would be basically shifting somewhere over here, because now this is my x plus h value, right? Because this was originally x and this is x plus h, because this distance is now h. So this green point basically shifted from here to here. And what effect would it have on the pink secant line we just drew? So the pink line would basically tilt in this manner. The pink line just shifted and tilted into this new pink line I have just sketched over here. Let's call this line 2 and this line 1. But basically the expression didn't change, because still now we haven't changed this h. The h was also called over here. The h was also called over here. So it means that the h hasn't changed, but we have decreased h, right? So how do we account this? Because here h was a large value and now h is a smaller value. So what if we take a limit and we say that what happens when h is approaching towards 0? What happens when I say that what happens to this whole expression when h is going closer and closer to 0? So I have sketched here a new diagram, basically the same diagram, just I've shortened the h value. And as you can see that instead of h being here, h has shifted over here, right? H has shifted over here. Now let's just connect those 2 points. One is x comma f of x, and this point, which is, so this pink line basically now shifted to this new pink line, and the slope has changed. As you can see that the slope has definitely changed, because previously we had seen that this h distance was very big. So the line was like this and the slope was something, let's say m1. And when we have decreased the h, when we have reduced this height to a very small value, just for comparison, you can see that here the h was such a big change, whereas h is a small change in x, all right? Because h over here is just this much change in x. So for that reason, that point was initially over here, that point shifted over here. So as you can see, when we are trying to reduce the value of h, when we are making the value of h smaller and smaller, this pink line is starting to behave like a tangent, right? Because just to recall, a tangent is basically a line touching a curve at a single point. For example, if this is a curve, the tangent to the curve would be something like this, a line that would touch the point at exactly a single point. So if this h, instead of being this much, if this h became more smaller, let's say h became approximately equals to 0. If this happened, then definitely that pink line would basically become the tangent at this x equals to x point. So that's our target. We want to find the tangent gradient at a particular point, because normally in coordinate geometry we had learned that if we had a line we could easily find the gradient of that line by using the gradients formula, but the problem arises when we have a curve, because the gradient at every point in a curve is determined by the tangent at that point. So similarly, what we are trying to accomplish is we are trying to figure out how can we find the gradient of that tangent at a particular point. So using the concept of limit that we have just learned a few moments back, we could say something like this. We could say that limit as h becomes approximately equals to 0 for the expression f of x plus h minus f of x divided by x plus h minus x. And this was basically the expression that would give us the gradient of the pink line. And what we were doing is we are basically trying to make the h approximately equals to 0 so that the pink line behaves like a tangent of the curve at a particular point. So when h becomes approximately equals to 0, this whole function would become this whole function would represent the tangent's gradient, and hence the answer to this limit would basically give us the gradient of a curve at a particular point, right? This would be the answer we were looking for, and this is what we call a derivative. A derivative is basically a measure that tells you the rate of change, which means that when x changes by 1 unit, how much does y change by? Similarly, you know from coordinate geometry, if you have a straight line, the slope del y by del x gives you the gradient, right? Del y by del x gives you the gradient. And in this case also, this expression we have just formed, this expression also gives us del y by del x, but instead of a particular line, this del y by del x expression is specifically for a curve. All right. Now the interesting thing is that as this is not a straight line, so the gradient won't be constant throughout the curve, the gradient won't be consistent throughout the curve. We could say that the gradient would be something like this. For example, if I just draw a random graph of x squared, y is equals to x squared, y is equals to x squared would look something like this. You could see that the gradient is going to change at every point. For example, when x is at this point, the tangent is something like this. And then when x is at this point, the tangent is something like this. So definitely this tangent over here, let's say this is tangent 1 and this is tangent 2. Both of these tangents have different slopes or gradients. So we can basically conclude that a curve, a non-linear curve, would have different gradients at different points. So to figure out a general formula for figuring out the gradients of a curve, we need an equation to represent this gradient. And that equation which represents the gradient of a curve at particular points is what we call a derivative, right? So a derivative is basically an equation that tells us the gradient, or you can say the rate of change of a curve at different points in the curve. So let's recap what we have just figured out. We had figured out that the gradient of a curve at any point can be given by this expression, which is limit as h approaches to 0 for f of x plus h minus f of x divided by x plus h minus x. And if you simplify this, you would see that this is f of x plus h minus f of x divided by, because this x cancels out and you remain with an h. Now you might say that we are saying that as h approaches to 0, this function won't be defined, because you can see that when we put h as 0, this whole thing would be something divided by 0, and something divided by 0 is undefined. So as this problem arises, we use the concept of limit, because we just discussed that we are not trying to figure out the exact value at that point, because it isn't defined, but we are trying to see that what this gradients expression is trying to go towards. Like when h is trying to go towards 0, what is the gradient trying to be? So that is our target over here. Now at this form, this expression isn't of much use, because we can't really figure out something from this expression directly. But what we can do is we can use this expression to find the gradients equation for different curves, and that would be for the next video.